Alright, first let's get to know our product. Our product for this assessment is shoes. We all know that shoes is designed to protect or support our foot while walking, running, or doing other activities. Without shoes, our foot could get hurt just by walking around the street. So, shoe is basic need. Let's look at the basic part of the shoes. The basic part of the shoe consists of sole, insole, outsole, and laces. Most of the shoes has these 4 basic parts. Either they are sports shoes, casual shoes, boots, and so on. From here, we can see that some shoes has their own use, but due to the environment temperature in Malaysia, some people might not be comfortable to wear a work shoes in the freezing cold office, or running with a sweaty foot from wearing a sport shoes. Because of this situation, we had the idea to design a shoes that could be worn in all situations. Let me introduce our invention product, which is temperature control shoe sole. This product has 6 modifications. First, the addition of temperature sensor. From the thermal equilibrium and temperature measurement, this shoe could detect the temperature of the foot and the environment effectively. Second, the addition of heating mechanism. Using the Joule heating and conduction mechanism, heat could be transferred to warm the foot. Third, the addition of control unit. Using the thermodynamic regulation, we could decide whether to turn heating or cooling on or off. Fourth, the addition of cooling mechanism. From the Peltier effect and the second law of thermodynamics, we know heat could be absorbed from food to make it cool. Fifth, the addition of insulation layer. From the thermoconductivity, we know that an insulation material will prevent heat or cool from escaping. And lastly, the sixth, the addition of power supply and battery efficiency. Using the energy conservation, we could use a rechargeable battery to provide energy to the system. From our invention, there are 5 component needs required to meet. First, what key need will you meet? Our key need is the need for active foot temperature regulation in extreme or variable environments. Second, whose key need specifically? These key need targets are athletes, hikers, elderly people, and doctors and nurses. Third, how often do people experience this problem and when? This problem occurs frequently, especially during long outdoor activities, occur in humid and hot climates, and occur in industry setting which has cold environments indoor. This is especially for doctor and nurse. Next, how big is the problem for users or customer? For example, in unwanted cost. There are several problems faced by user. First, medical cost. This is because some user could get frostbite, drenched foot, or heat-related injuries that can lead to expensive treatment. Second, productivity loss. Some people could not focus with a cool feet, or in some cases, that sweaty feet lead to blisters. Third, replacement cost. In this case, some socks might easily damage, or the shoes might not last due to the moisture damage. And lastly, what will happen if that need is not met? Alright, we need to consider the fact that first, user mostly will have physical discomfort that leading to reduced motivation or postponement in their activities. Second, serious health issue could occur like the frostbite or fungal infection. And third, user will usually increase their reliance on temporary solution. For example, using multiple layers of salts and chemical warmers, which are inefficient and environmentally wasteful.
Next, we'll be moving on to component of approach that we'll be using for the shoes that we want to invent. What is the unique approach that we will use? The approach that we will use is actively regulates foot temperature in the shoes. Feet will feel cold or hot depending on the user need while they are using the shoes. This will make them feel more comfortable while wearing it. We will use the concept of Joule heating and Peltier cooling. This can be controlled via apps in smartphone or manual control on the shoes. For the first concept, Joule heating, it is also called as resistive heating or ohmic heating. It occurs when an electric current passes through a conductor, either liquid or solid, with limited conductivity. It can convert electrical energy into heat. The formula for this concept is Q equal to I to the power of 2 times R times T, which is Q is heat generated in joule, I is current in ampere, R is resistance of the conductor in ohms, and T is time in seconds. For the second concept that we will use is battery cooling. It occurs when a current is passes between two different conductive materials, usually semiconductors, which one side will absorb heat, it gets cooled, and the other side will release heat and it will get hot. For more detail about the concept that we'll be using, I will pass to Atira to continue the presentation.
Next, I will be explaining what is our solution. The first one is smart insole or midsole. Second one is user interface, and the third one is design for comfort and durability. So first, I will be explaining the first solution, which is smart insole or midsole. The foundation of the solution lies in a modular embedded system built into the shoe insole or midsole. This system composed of several key components that work together to provide dynamic thermal regulation. So the first one is heating system, Joule heating element. Utilize resistive heating wire or carbon fiber filament. Position near the toe and ball area of the foot for maximum warmth where blood flow is lower. Safe temperature range 30 to 45 degrees Celsius, regulated by sensor to avoid overheating. Next is cooling system, Peltier thermoelectric module, optional in premium model. Peltier effect allow for active cooling by creating a heat flux between the two materials. One side of the module cools the foot, while the other side expels heat to the sole outer layer, and it requires effective heat dissipation and thermal insulation layers to prevent reverse heating. For user interface, there are two main points that I will elaborate. For the first one is mobile app integration. Allow user to manually adjust temperature, display battery level, foot temperature and preset mode. And apps connects via Bluetooth low energy BLE for minimal power draw. And the second point is manual control. On shoe touch or pressure sensitive button for toggling modes, and ideal for users who prefer not to use smartphone or when phone battery is low. Next, I will be going for the last point. So the last point for the solution is design for comfort and durability. The 2 points that I would like to elaborate is the first one, which is flexible impact resistant material. Heating or cooling components are sandwiched between EVA foam, TP or gel cushioning layer. Preserve the flexibility of the sole and does not compromise gait or movement.
Although these temperature-controlled shoe soles offer great potential in terms of comfort, health and performance, there are several critical technical issues that must be addressed before this innovation can become a viable and market-ready product. The challenges include waterproofing, power efficiency, cost, weight and comfort, durability, and thermal management. The first challenge is waterproofing. The environment inside a shoe is not ideal for electronics. There is constant exposure to sweat, humidity, rainwater, or even spills. To ensure safety and reliability, the entire electrical system must be sealed and waterproof. This includes using waterproof membranes, seal connectors, and moisture-resistant coating on PCBs. Without this, even a small amount of moisture could lead to corrosion or short-circuiting. The next challenge is power efficiency. Heating and cooling systems inside a shoe sole require a considerable amount of electrical power. Heating uses Joule heating principles, where electric current passing through a resistive material generates heat. Cooling, especially using Peltier modules, also draws significant power and has additional thermal losses. Therefore, one major challenge is optimizing power consumption to ensure that the battery lasts long enough. Ideally, a full day without being bulky or needing constant recharging. We need to explore a high capacity yet compact batteries, efficient circuit design, and smart power saving modes that adjust heat output based on actual user needs or ambient temperature.
The third challenge is cost and scalability. Adding smart heating and cooling features, sensors, and battery packs increases production costs. For widespread adoption, the product must be affordable. That means selecting cost-effective materials, designing for mass production, and possibly offering multiple product tiers. For example, basic models with heating only and premium versions with both heating and cooling. Balancing innovation with cost efficiency is crucial to make this product accessible not just to niche users but also to the broader consumer market. Next, weight and comfort is also one of the challenges. Shoes are worn for long periods, so comfort is non-negotiable. Adding electronic components such as wires, sensors, batteries, and heating elements must not interfere with the shoe's flexibility, softness, or natural foot movement. If users feel a lump, imbalance, or heaviness in the sole, the product will not succeed commercially. Thus, the design must ensure that all components are ultra-thin, lightweight, and evenly distributed, maintaining the ergonomic and cushioning aspects of regular footwear. Next is the durability. Unlike other wearables, shoe soles undergo constant bending, pressure, and friction during walking, running, and standing. Components must be rugged enough to survive these mechanical stresses repeatedly. Any wiring or sensor must be flexible and resilient, possibly using flexible printed circuits or woven conductive fabrics. Furthermore, the system must resist shock from impact and avoid short-circuiting due to wear and tear over time. The last challenge is thermal management. While heating the food is relatively straightforward using resistive elements, cooling is more complex. Lithium modules can cool one side but release heat on the other. If this excess heat is not properly managed, it can build up in the sole or battery compartment, leading to user discomfort or component failure. Therefore, an efficient heat dissipation mechanism such as built-in heat sinks, thermal insulation layers, or phase change material must be integrated to ensure safety and performance. In conclusion, temperature-controlled shoe soles solve a common and serious problem such as cold or overheated feet by offering a smart, comfortable, and scientifically advanced solution. Using embedded heating and cooling technology, they actively regulate foot temperature, improving comfort, health, and performance across various environments. Whether for outdoor workers, athletes, or people with circulation issues, this innovation meets a real need with practical, durable, and user-friendly design. That's all from us. Thank you.